Hey everyone, welcome to the Zimmersec channel. Today we'll be learning a fundamental task that every digital forensics investigator and cybersecurity professional needs to understand: computer file structures and how to analyze disk images using command line utilities. And whether you're starting your journey in digital forensics, preparing for incident response work, or just curious about how data is actually stored on your computer, this tutorial will give you hands-on experience with real forensics tools used by professionals worldwide. But before we jump into the tools, we need to understand what we're actually looking at when we analyze a disk image. The first question we want to ask is, what is a disk image and where does it come from? Well, a disk image is just a digital copy of a file system. This can be just a single partition or the entirety of a drive in the form of a single file. There are many hardware and software utilities that could help you create a disk image in very little time. One that comes standard with Linux distributions is the DD utility, and there are countless other Windows options available out there for you to look at. Now covering on to some key concepts. What is a file system? You may be all very familiar with this, but a file system is essentially the organizational structure that an operating system uses to store and retrieve data from the device. Think of it as a library catalog system. It keeps track of every piece of data that lives on your disk. And while you might run across all different types of devices and operating systems in the world, the most common file systems that you're going to find on those devices are going to be NTFS. It's the new technology file system found on modern day Windows devices. ext4, which is going to be the most common on Linux systems. APFS, or Apple file system, and HFS is going to be used on Mac OS devices. And then mobile, like removable media or USB drives, are going to use the FAT32 or the exFAT file system structure. And it may be a little overwhelming to try and keep track of all these different file systems, but every single one of them is going to have the same few critical components. Starting at the base, you're going to have the boot sector, or sometimes called the superblock, which contains metadata about the file system itself. And the very first sector on the storage device that contains machine code necessary for the loading of the operating system. The second part is going to be the file allocation table, or the inodes, which track which blocks belong to which files. Directory structures is going to be the next one up, which actually is the organized file hierarchy that you interact with on a daily basis. The next component is just considered the data area, and it's where the actual file content is stored. And separate from the actual data content, we have the metadata, which is the information about the file itself, and this includes the timestamps, the permissions, the file size, the file name, those things that aren't actually the content within the file. And you might be even wondering why this matters to forensics in general. But understanding these structures is really important because sometimes deleted files often leave traces in the metadata areas, and even when it is considered deleted, data might still be found on disk and only the pointer to it gets removed, allowing us, the investigators, to possibly uncover those potential artifacts. Now that we understand the basics of a file system, let's talk about how we can go about analyzing an image that we've been provided. We can use a tool called the Sleuth kit to begin analyzing a file. So a little overview about the Sleuth kit, or TSK. It's an open source collection of command line tools for forensic analysis on disk images. It was created by Brian Carrier and is used for forensic investigators, incident responders, and security researchers worldwide. So what really makes this powerful is that it can analyze file systems at a low level, meaning we can recover deleted files, examine hidden data, and extract artifacts that normal file browsers can't see. Just before we jump into the tool, I want to talk about the way in which SleuthKit organizes analysis into 4 distinct layers. It's very important and will give us a better understanding of how the commands will be used. The first layer is the media layer. This includes the high-level metadata related to the sectors or partitioning of a drive, and the commands used to interact with it start with MM. The second layer is the block layer, which is a sequential list of fixed-size logical blocks containing the real data. The commands interacting with this layer start with BLK. The third layer is the inode layer. Inodes may be a part of the ext4 file system, but it's equivalent to FAT32's file allocation table, or FAT, and NTFS's MFT, or master file table, as we discussed earlier, where a single inode number will help us by mapping out where the data blocks our file's actual contents are stored at. The commands interacting with this layer all start with the letter I. The fourth layer is the file name layer. This is the nice printout of the file system that you normally interact with on the day-to-day with dir or ls. You can navigate through directories and use them to reference files' inode numbers for further analysis. This layer can also maintain data for deleted files. The commands that all interact with this layer start with the letter F. There are more than just 4 layers, but since this is just a brief introduction into the tool and how to use it, those studying for GCFE or the NCE should research deeper into the other layers. Now, with all that said, let's jump into our lab environment. After transitioning to our desktop environment, I'm going to open up and use a hypervisor to launch an instance of Linux Mint. This is preferably one of my favorites, which already has the image file loaded onto it. This could be a .dd file, it could be whatever you use to extract that disk image. I'm going to open up a terminal, and knowing that this distribution does not come with the Sleuth kit installed, I'm going to have to raise my permission with sudo apt install, and we're going to do Sleuth kit. Enter our password. All right, now that it's done installing, we can begin to analyze this disk image. Okay, after increasing the terminal size so it can be a little easier to read, we can begin to examine our partition layout using our first command, which is going to be mm, which, as we remember, is going to be the media layer, which is going to be that high-level overview of the partitioning tables. Right, mmls, which is just going to be list the media layer, just like that ls command. Then we can add on our image file, which is going to be ext4.image. So right away, this is a lot of seemingly confusing data, but what this tells us right off the start is what kind of partition table this is. And we see it's a DOS. Another option you may see is going to be a GPT. So we know that offset starts at 0, and these are all going to be 512 byte sectors, which are going to be those block sizes. So starting at 0, we see that there's a 1 byte primary table, really not doing a whole lot there. But picking up from that non-existent byte is going to be 2047 byte long or 2048 byte long unallocated unused memory space. After that, picking up from that memory location, it's going to be another 204,000 byte long partition ending at this address, which we know is Linux, probably ext4. What I suspect is that this is going to be the bootable or the boot sector of the file system. We can tell by the swap word here, this is probably just a swap partition for the previous boot sector. We know this because they're both the same exact size. And then we get down here to the longest in length partition, which is going to be over 400,000 bytes long. The Linux, we know it to be ext4 partition that starts at memory address 411,648. What is really important out of this is that you understand where each one starts and how long it is, the ending point, not so much, but mainly this first offset here is going to be very influential in the commands we run following this. Going forward, I know we didn't really talk about the file system layer. We talked about the file name layer, but we have another command here that we can use in order to give a comprehensive overview of the information on the file system structure. And that command is just going to be fss stat. So fs stat. I don't know why I said it like that. But what's important here, like I was talking about just a second ago, is the offset in which we want to identify a file system. So we know this is most likely going to be the main partition with the main file system attached to it. In order to point our command at this exact partition, we need to reference this offset number. Doing so with just the TAC-O flag option, whatever you want to call it. So using TAC-O to reference that offset, we can say 411648, right? And then we still have to point it within our image file. So using this command, tons of data. From this, you're going to see a lot of block ranges, inode ranges. You'll see a lot of timestamps, and why those are important to us is the general use case for timestamps being that they tell us when the system was set up, last accessed, etc. But let's get back down here. Now we can start to look at one of the more powerful features of this tool, and that's going to be just starting to list and explore all the file names of the file name layer. And we do that with the F character like we talked about, but it's going to be FLS to list the files. And again, we have to go again and reference that offset number, which we'll just do it here. Go back and change this to FLS. Run the command. Perfect. It looks exactly how we thought it would with an ext4 file system, like file hierarchy. We have the usual home directory for user accounts, roots folder, we have the swap file, and a couple of others we might see. But another functionality is that this acts just like an ls command. While we might be able to just do fls help, and it'll dump out all the available options, we see that it has attack a switch, which allows us to list all entries, including hidden, and the logical reference address. So going back up to the output of our original FLS command where we list just the base file structure of this image, we see a couple things here. We see our directories. These can change and tell us if they're files or not. If they're files, we can begin to look at those files and maybe use the cat function of this. We'll get into that later. But we can use further functionality to look at those files and pull out the block data from those specified inodes. So where are those inodes? And it's right here. These numbers are the inode numbers that we can go ahead and reference in order to further investigate that folder or that file with different utilities. Knowing that, let's go ahead and use our utility. We'll just up arrow again. I'll add on the tag A to see if there's any hidden files by chance. And we'll go ahead and look and reference the home inode number. So we just throw that, numlock, 460 on the end. What we see here is there's the current and then the back directory. It's empty. There's nothing in it that we can find. But what I do know is that this image file comes from a CTF event with a known flag.txt file inside. And just like I was saying before about how this acts just like an ls command, there's going to be that tag-r option within it in order to recursively search across the whole file structure. So we can build out a command here, tag o, tag r, after the A to show us all the hidden files as well. And then we can couple that functionality with grep in order to search for, flag, right? And that'll go across all the files. It'll tree out every directory inside the file system from the base layer and find us all mentions of the word flag. So now that we've found a file of interest that we kind of want to look a little more into, maybe a deleted document, we can extract it using the icat command. But before we do that, I want to show you something that's a little different between these two. Even though they're in the same directory, they have two different attributes here. One has a star here, and also this reallocation or the realloc next to the inode number. And what this is going to tell us is that this is a deleted file, right? So even though it still maintains its inode number, the memory space, the pointer has been removed, but there's still some data that could be recovered. While on the other hand, this other one here is a perfectly normal and existent inode and file that we can look into. And how we go about looking into that, you can use the icat, which is going to use the I here, which says we're going to reference the inode layer. We're going to do our offset. You know what? Yeah, icat taco 411648. So tell them our image. And then what we're going to do from there is give it the inode number, 1876. So what we see out of this is a lot of white space, and then what appears to be coordinates. There could be anything in this file, but what we do know is that this is a deleted file. Looking at the other file, 1782, we see that it contains some salted, encrypted, unreadable content, kind of implied with the .enc. If we want to look further at that, really, we can output that to some file, or we'll just do the same name, flag text inc, and we can do file on that. And it shows that it's an open SSL encrypted text file, pretty much with a salted password. And we can go about trying to do all these different things to decrypt it. And I have a full write-up on this entire CTF here. It's called Operation Orchid. If you want to find it, it's on my GitHub. Feel free to go check that out if you want to walk through on how to do this. And then one final utility I want to showcase is another inode layer command that's called istat. Just like the fs stat, it's going to show us everything it knows about a certain file. So if we want to use this on this hidden file here, we're pretty much going to do the same exact syntax where it's istat TACO 411648. I could type and then give it the image name. And then we can do 1876. We see that inode number is 1876. This is allocated memory space. We got the UID, group IDs. We got the permissions on it, any different flags, the size of the file, the MAC times here, which show us a lot of detailed information about when it was accessed, created, last modified, all those things. But one thing I want to show you is that it's powerful in the way that you can just, with one small command like this, skim through an entire file system, find what you want, and kind of go from there to quickly analyze something. There's like, I'll give you the end, right? When you don't grep for flag, you see where the file actually comes from. Oh, here it is. Flag.txt. We see that it's a part of the root home folder as hidden, as non-hidden files. But what else is in that root folder is a shell history. So if we take this, we just icat, use our icat commands. Take a closer look at that. We can see that it provides, the OpenSSL decryption password in order to access that flag for the CTF. As we go to wrap up this project, I want to talk about some critical best practices when it comes to analyzing evidence files. First, you always want to work on a forensic copy. One wrong command can alter timestamps, data, and really mess up your chain of custody and the integrity of the evidence. While analyzing it, I want you to keep detailed notes of every command you run, every artifact you find, and all the context surrounding the finds. When it comes to upholding your testimony in court, this is going to be what's really important. Read the man pages, experiment in safe environments, and never just assume what the evidence actually suggests. Like I said earlier, when it comes to professional forensics, maintaining that chain of custody is critical. Know how to document who had access to the evidence and when. With that said, I want to close out the fundamentals to disk image analysis with the Sleuth kit. Hopefully you've learned the basics to how a file system organizes data, how it examines disk images at a low level, and how you can list files including deleted ones, recover content, and extract crucial metadata. These skills form the foundation of digital forensics work, whether you're investigating security incidents, performing data recovery, or just want to know how your computer really works. These techniques are essential. If you found this helpful, please be sure to drop a like and subscribe. If you have any questions or comments, please drop them in the comments. I'll be diving deeper into advanced techniques, timeline analysis, and other forensics tools in upcoming content, hopefully. Thank you for watching.